Hey guys, IBM is here to bring you another episode of Learning Physics. I am recording Physics 9702, Paper 5. This is Planning, Analysis and Evaluation. This is October-November 2022, Paper 5-2. So without wasting time, I would like to take to the question paper. So this is the question paper that we are going to solve. It is 970252 October November 2022. The paper is supposed to be 1 hour and 15 minutes, but I may take more time because it involves drawing diagrams on the question on my HP computer. Therefore, it may take some time. Of course, there are some teachers whose work is to just criticize my content. Please, you can always start your own YouTube channel and try your level best to also do the same thing or even better than mine. For students, I think you should always be learning something from my videos. I don't mind about your comments. You can always raise a question, send your question so that I can try to clarify anything you want. So question number 1, a thin copper sheet is suspended from a small hole. This is almost the same as 5.1 that I solved recently, but slightly different. And placed in a magnetic field. So we need a magnetic field. I'll use a horseshoe magnet for a magnetic field. Because it's suspended, I'll try to find something that I would use to suspend this. Maybe I would use, I may use a thin metallic rod. I'm going to use a thin metallic rod to suspend this. So I'm just drawing the skeleton of my diagram. So I'll use a thin metallic rod to suspend this. And I will of course clamp this. So I'll put a ruler here. I will put a stand here. I will have to clamp this. So I'll use a clamp to hold this on the stand. Then the sheet has area A and thickness Z. So to measure the area, I will need length times the breadth, and this one will be measured using a ruler. To measure the thickness is always something which is really small, so I may use a micrometer screw gauge. And of course, here I will need the average. So it means I will take the thickness at different points around the sheet or at different positions around the copper sheet so that I obtain the average value of Z. Then the sheet is displaced from its equilibrium position and then released so that it oscillates perpendicular to the magnetic field. So I'm going to put a magnetic field. So I may have maybe that is the North Pole. I may have the South Pole somewhere. So this is going to be a horseshoe magnet, North maybe and South Pole. So the sheet is going to oscillate between the North and South Pole. Okay. Of course, because it is a metal sheet, we expect that the edges could be sharp. So I could use gloves for safety. I may use gloves, and also I could put a sand tray here at the bottom, just in case. I could put a sand tray at the bottom just in case the copper sheet falls off. It just falls onto a sand tray. That is a safety precaution. So the time t when the sheet is released to when it becomes stationary is measured. So I can use a stopwatch for t, stopwatch. Of course, for this one, I can't take it. I can repeat and obtain the average. I can repeat and obtain the average. So I'll measure t using a stopwatch. So it means t cannot be the independent variable because I can't change t myself. But I can change the thickness. I may vary the thickness. I may use a copper sheet of a different thickness. So Z is going to be the independent variable, which I will change myself as the examiner, and T is going to be the dependent variable. It is suggested that T is related to Z by this relationship. T is Kz power Q over AB rho. B is the magnetic flux density. Remember, to measure, I need to measure the magnetic flux density and should remain constant. So here I will use a Hall probe. And remember, every time you use a Hall probe, you first measure in one direction, then in the opposite direction, and get the average. So average is very important. Then rho is the density of the copper. So since rho is the density, and K and Q are constant, so rho is going to be rho is going to be a constant, because the density, of course, is going to affect. If it is not kept constant, then it may affect the result. So I'll ensure that the density is constant, but density, remember, is also m over v. The density of the copper is m over v, so I must use copper of the same density. So it means I will need the mass. Of course, to measure the mass, I'll use a balance. The volume, since I have the cross-sectional area, I'll measure the volume from area times Z, where Z was the thickness. So I'll get the volume from area times Z. I'll measure the mass using a balance so that I find the density of the copper sheet, and should be the same thing. Should be the same density. So plan and laboratory experiment test the relationship between T and Z. Draw a diagram. I will draw the diagram. Explain how the results could be used to determine our values for K and Q. So this is going to be analysis. For analysis, I must make the independent variable or anything. The dependent variable should be the subject, and it is already T. So because Z is to power Q, I must introduce ln or log. So I will say ln of T, or you can say log of T, is going to be equal to the log of Z power Q plus or times, sorry, this is plus the log of capital K over A B times rho. So I'm going to simplify this to be log of T equals to Q log of Z plus log of K over A B rho. So this is going to be a straight line if I plot log of T against log of Z. So I'll plot a graph of log of T against log of Z. If I compare with y equals to mx plus c, it means the gradient, which is m, is going to be equal to q. So they said we should show how to determine q and k from the y-intercept. The y-intercept is going to be the log of k over a b rho, which means if I want k, I must first of all find 10 to the power of the y-intercept, and that is ant log, then times a times a b rho, or you could find e to the power of the y-intercept, that is if you introduced ln, because ln is natural log. So I've mentioned the procedures, the measurements to be taken. The control variables are those ones which should be kept constant. For example, the area affects the value, so it should be constant. Magnetic flux density affects the value, so it should be constant. And I think even the density the density of the metal sheet should also remain the same throughout. Then analysis, this is which graph should be plotted. Safety precautions, I said since it is a metal sheet, we are prone to cuts. So to avoid cuts, I will use gloves to protect my hands from cuts from the edges. And I've also added a sand tray at the bottom, so that in case the metal sheet falls off, it just falls into the sand tray. That is for safety. Okay. Then because I'm going to time, because I want to The sheet is displaced from its equilibrium position and then released so that it oscillates perpendicular to the direction of the magnetic field. So I need a reference point, so I may put a vertical pin somewhere aligned with one of the edges so that displacement always occurs from the same position, or displacement occurs to the same distance, because I don't want it to displace to a longer distance than before so that it affects the values, it affects the time it takes to reach rest. So because I must measure the distance through which it is displaced, so I need a reference pin somewhere which is aligned with one of the edges, and I will need a ruler so that I always displace to the same distance. So I'll put a ruler here. So I'm just going to clamp the ruler somewhere here. This time I'll put the ruler behind the other side. Okay, so I'll need a ruler so that I always ensure that I displace this through the same distance. Okay, so in this experiment, now I can write the essay. In this experiment, we have said that Z is the dependent variable. I mean, Z is the independent. Z is the independent variable, and T is the dependent variable. Then we mention which quantities are control variables. So you don't say this and this is the control variable. You should say this and this should be kept constant. So I will say I will keep B and A constant. By the way, there are three free marks for analysis. I could even skip that stage. And first of all, I will go to the last and I write for safety. What is I said for safety, I mentioned two things, so I can write here for safety. Number one, I said I will place sand tray below the sheet, just in case the sheet falls. That is safety. I've also said I will also use gloves to protect the hands. To protect hands from the cuts, due to the sharp edges. Okay, that is always one mark. Then the other one, I can also write analysis somewhere here. I've already seen which graph I will plot. So I don't want to follow the order so that students can know how easy to get some of these marks. You know which graph you're going to plot, and if it is going to be a straight line through the origin or not. So I'll just write here that I will plot a graph. And we have already seen which graph we shall plot. So I will plot a graph. I'll plot a graph of log t against log z. And we say the relationship is valid if it is a straight line The relationship is valid if it is a straight line. It had a y-intercept, so it doesn't go through the origin. Relationship is valid if it is a straight line, not passing through the origin, not passing through the origin. Those are two marks. Then we are still on analysis. We have to find K and Q. Remember, Q was equal to the gradient. That is another mark. And then K, I think we said what was K. K was equal to 10 power the y-intercept times AB rho. So I'll just add it here. K equals to AB rho times 10 to the power of the y-intercept. So already here, this is 1, 2, 3, 4, 5 marks. At the bottom there, those are 5 marks. Then you add these 2, 6, 7 for stating which one is independent and which one is independent, and the ones which are to be kept constant. I've not even drawn the diagram. So I said I will keep B and A constant. Then I can mention some of the measurements I will take before I set up the apparatus. So I will use a ruler. I will use a ruler to measure lengths. This is a plural, that is could be length times width. They are just lengths. Length of the sheet to determine the area from. So the area is going to be equal to the length multiplied by the breadth. Okay, so I have determined the area of the sheet that I'm using. Then number 2, I have to measure the thickness of the sheet. So I will also measure Z, which is the thickness, using micrometer screw gauge. So I will also measure Z using a micrometer screw gauge. But of course, this is going to be in different points, in different positions. Of the sheet and obtain the average. And obtain an average value of Z. Okay. I think I should also measure the magnetic flux density before I set up my apparatus. I will also measure, oh, by the way, I need to measure the mass. I will measure the mass of the sheet with a balance and obtain its volume because I've already got Z and the area A. So I will measure the mass M. I don't even need to introduce another letter. Let me leave the letter. I'll measure the mass of the sheet with a balance It can be a beam balance, electronic balance, and so on and so forth. So I will measure the mass of the sheet with the balance and also obtain the volume from, since I have the area, so from volume is equal to, we have the cross-section area, we have measured Z, so volume is going to be equal to cross-sectional area times Z, and determine density, determine density rho. From rho is going to be the mass divided by the volume. So this statement I've written here has almost 1 to almost 3 marks in one statement. Some of them are additional points. Okay, so now I know the volume. I've measured the volume. Now I know the density of the sheet that I'm using. Then the next step, I must measure also the magnetic flux density, because B should also remain constant. So I will measure B using, of course, magnetic flux density, I say it is measured using a Hall probe. So I will measure B using a calibrated Hall probe. A calibrated Hall probe. You must have mentioned the Hall probe in magnetic fields. And how do we use this? I said we always measure. I'll measure B using a calibrated Hall probe between the poles of the magnet. First in one direction, and then in the opposite direction. And then in the opposite direction and obtain average of B. Okay, so I have now to set up the apparatus as shown in the diagram. So I will now assemble. So because I don't want to displace the copper sheet through a larger distance, I want the distance through which I displace to be constant, because if the distance changes, it means the time it takes to go to rest will be different. I will need a ruler. I will clamp a ruler somewhere so that measurements are always taken from for the same distance of displacement. Okay, so now I'm going to draw my diagram. So I will start with the table. So let us assume the setup is on a table. Draw the diagram with a pencil and make sure it is neat. Where possible, use a ruler. So this is going to be the table. So I'm going to put here my cushion or the sand tray. Let me first draw the clamp. I mean, this is the stand, not the clamp. Then I'll put the sand tray somewhere here. So that is the sand tray. Let this be the stand. Okay, so now I'm going to put I wanted to clamp a ruler behind on the other side, so I'm going to put a ruler. Okay, let me draw whatever is this side. I'll first draw the sheet, copper sheet here. Okay, you can draw a better diagram. So I'll put a hole somewhere here, and I'm going to draw a wooden rod through, which is going to be clamped. So let me first draw the clamp. So this is a clamp, and I'm going to assume it is holding a wooden rod. Not a wooden rod, I want to use a metallic one. Okay, so this is going to be the rod. Okay, I'm going to add a ruler because I want displacement to be through the same horizontal distance. So I'll put a ruler here. So this is going to be the rule. It is a meter rule. Okay, so I'll label this. This is the copper sheet. And of course, I'll label the hole here so that it is visible. Then I'll put some marks here to show that this is a ruler. So because I want to displacement always be from the same position, I may put a mark which is aligned with, so instead of a mark, I'll put a pin. So I'll put a pin which is aligned with one end of, so this is a vertical, this is going to be a vertical pin. The vertical pin is aligned with one end of the copper sheet. The next is, what is missing is the magnet. So I'm going to put poles of a magnet. So I'll put one pole the other side. Let's say it is the north pole. I don't need to make it very big. Then I'll put one pole here. Okay, you can draw better magnets. So I will label this south, and I may label that one north. So this is going to be a horseshoe magnet. Okay, so I've tried my level best, I think, to make this look nice, or maybe I can rub off this part and draw it so that it is inside. It is on the other side. So Okay, so I try to make my diagrams look very beautiful, but you can draw something that is reasonable. You may not draw exact, you may not think exactly the way I think because me, I'm a teacher, so, but still, it you can have a good diagram. Okay, I think I've tried to exhaust everything that is necessary for this experiment. I have a suspended metal copper sheet, I have a magnet, horseshoe magnet, I have a ruler, and I have a vertical pin from which a displacement will always be taking place. The ruler is to ensure that I always displace the copper sheet through the same distance so that I don't affect my results. Okay, so I will assemble the apparatus as shown in the figure above. So the first thing I'm going to do is I'll line up the corner of the sheet with the vertical pin and then displace it through a distance which is going to be measured from the ruler. So I will say I will initially line up the corner of the sheet with a vertical pin which is going to act as a reference, and then displace it through a horizontal distance measured from the ruler. So this displacement of the copper sheet must remain constant. The displacement of the copper sheet, so let me say the initial displacement, I will displace it through a horizontal distance measured from the ruler. The initial displacement of the copper sheet should always be the same. So we should always displace the different copper sheets through the same distance. Now next is I'm going to measure, of course here I'm using a stopwatch to measure the time. So I will measure the time t. I'll measure the time t using a stopwatch. From release until oscillations stop completely. Okay. Of course, every time you take a measurement involving time, it's better you repeat the measurement because here we're not timing oscillations, but we are timing when it stops. So I'll repeat the experiment for each z and obtain an average value of t. I'll repeat the experiment for the same value of z and obtain an average value of t. So the next step is just now repeating the whole process for different value of z. I will now repeat the experiment for different values of z until I have 6 sets of results. So until I have 6 sets of results. So the next thing here is now going to be plotting a graph. So I'll plot a graph of log of t against log of z. I've already gone through this. Okay, so I think that is enough for this experiment. This is enough for this experiment. I think every marking point has been involved here, or most of the marking points. It could be not all, but most of them are actually more than 18 marking points have been given here, and the examiner will only look for 15 marking points. Okay, so that is part question number 1. Then let's see question number 2. A student investigates stationary waves in a vertical tube using the apparatus shown in the figure. So this is the apparatus. The student slowly increases the frequency of the signal generator from 0 and listens to the sound. Loudness of the sound varies several times between minimum and maximum. As the frequencies increase, the lowest frequency giving maximum loudness is identified by n equals to 1. The next frequencies giving maximum loudness are identified by n equals 2, 3, 4, 5, and 6. For each value of n, the student observes the trace on the oscilloscope screen. The student measures the distance d on the screen between two successive crests. Okay, d is the distance between two successive crests. Of course, the distance between two successive crests is most likely going to be wavelength. The student then determines the period t and the frequency f of the signal. It is suggested that f and n are related by the equation. F is equal to that, where c is the speed of sound in air and h is the height of the tube. A graph is plotted of f against n. Okay, so I must make sure f is the subject, and I must make sure that I break down n so that it stands alone. Determine an expression for the gradient and y-intercept. So I'm going to break down that equation. So f is going to be twice nc over 4h minus c over 4h. I've opened the bracket. So it means f is going to be twice c, 2c, this is going to be 1 over. 2 over 4 is a half, so this is going to be, I'll just write a half, or I'll write c over 2h times n minus c over 4h. So when I compare this with the general equation of a straight line, y equals to mx plus c, on the y-axis I have f, on the x-axis I have n, so it means the gradient is going to be c divided by 2h, and the y-intercept is going to be negative of c divided by 4h. The period t and the frequency f are given by the equations. T is equal to d times the time-base setting, and f is 1 over t. Values of n, d, and t and the time base of the oscilloscope are given in the table. Calculate and record values of t in milliseconds and f in hertz in the table. Include absolute uncertainties in t and f. So remember, t is equal to d times the time-base setting. I'll call it x. So t is d times x. So we maintain the number of significant figures. Now note that the time base is a constant. So I'll just take at least two significant figures which are determined by D. So you could have more significant figures, but I'll use those of D. So I'll say the first one is 1.5 times 5, which is T is D times the time base. Okay, so it is 1.4, not 1.5 times 5, which is 7. So I'll write here 7.0. Here I'll just say 1 times that, which is 2.9. 0.5 times 3.6, that is half, which is 1.8. 0.5 times 2.7, that is half, which is 1.35. I'll write 1.4. Then 0.5 times 2.1, that is 1.1, two significant figures. Then 0.1 times 8.8, I think it is 0.88, two significant figures. Then I'll also find the uncertainties. The time base is a constant with no uncertainty. D has its uncertainty given, so it means the absolute uncertainty in T is going to be a constant times the absolute uncertainty in D. Because the time base is a constant number, so I'll just be multiplying the constant by the absolute. So the first one is 5 times 0.2, which is plus or minus 1. The second one is 1 times 0.2, which is plus or minus 0.2. The third one is 0.5 times 0.2, which is the same as plus or minus 0.1. 0.5 times 0.2, which is plus or minus 0.1, plus or minus 0.1, plus or minus 0.02. Okay. Then uncertainty, include the absolute uncertainties in T and F. So now we are going to F. Remember, F is 1 over T. If T is to two significant figures, then 1 over F can be to two significant figures or more significant figures. For instance, the first one could be 1 divided by, remember this is in milliseconds, yet we want this in hertz, so I have to remove the milli. So it's 1 divided by 7 exponent minus 3. So that's 142. So I can either write 140 plus or minus, or I can write 143 plus or minus. I will put 140 or 143 if you round off to three significant figures. You can increase the number of significant figures. Then the next one is going to be 1 divided by 2.9 exponent minus 3. So I can either write 340 or you can write 344. Is it 345 plus or minus? Then I will have the next one is 1 divided by 1.8 exponent minus 3. So this is either 560 to two significant figures, or you can write 556. Then the other one is 1 divided by 1.4 exponent minus 3, which is 710, or you can write 714 plus or minus. The other one is 1 divided by 1.1 exponent minus 3. So this is 910, or you can write 909. And the last one is 1 divided by 0.88 exponent minus 3, which is 11,000. No, it's 1100. Or you can write 114 plus or minus. So it's 1140 plus or minus. Then let's check the uncertainties. For the uncertainty, remember I've been calculating, this one has been f equals to 1 over t, and of course the absolute in f is going to be the absolute in t over t times f, times the value of f. So for the first one, for the first absolute in f is going to be the absolute in t, which is 1, divided by the value of t, which is 7, times the value of f, which is 140. So this is going to be 1 divided by 7 times 140. I'll round off this to 20. Alternatively, I could use 143, where I would say 1 divided by 7 times 143. So here it is still 20. The next one is going to be 0.2 divided by 2.9 times 340. So this is also to one significant figure, I'm just going to write 20. But of course, if I use 345, I can write 23. Then the next one is 0.1 divided by 1.8. You notice that here I'm not including the power of 10, because it is going to cancel out. The uncertainty and the true value have the same power of 10, so it cancels out. So 0.1 divided by 1.8 times 560. So this is 30. But when you use 556, you are most likely you can write 31. Then I have 0.1 divided by 1.4 times 710. This is 50. To one significant figure, it is 50. Or you could write 51 here. Then I have 0.1 divided by 1.1 times 910. That is 80. But you could also have 81 if you use 909. Then you could have 0.02 divided by 0.88 times 1100. This is 25, which is approximately 30. Or you could have 25 here. You can check the last one, 0.02 divided by 0.88 times 1140. It's approximately 26. Let me check the other one, 0.1 divided by 1.1 times 909. This is approximately 83, not 80. Let me check the other one, 0.1 divided by 1.4 times 714. That's 51. The other one is 0.1 divided by 1.8 times 556. That's 31. The other one is 0.2 divided by 2.9 times 345. This is 24. Okay, so that is just checking the other uncertainties, but I'm not going to plot them. So I'll plot these ones because they are even easy. Uncertainties are good enough to one significant figure. So plot a graph of f in hertz against n, include error bars for f. So we don't need error bars for t. Because f is on the horizontal is on the vertical, the error bars are going to be vertical. The error bars will be like this. Draw the line of best fit, the worst fit, determine the gradient. So we shall find the gradient of the best fit. and we shall find a gradient of the worst fit, and then we shall find the uncertainty, which we will be subtracting. So let's go and plot the graph. I'll write the points on a paper so that I plot very easily. Okay, so let's plot. I think plotting this is very quick. When n is 1, f was 140, so n is 1, f is 140. The scale on the vertical is 100 divided by 10, which is 10. 1, 2, 3, 4. That is 140. When n is 2, the other one is 340. 2 is 1, 2, 3, 4. 340. When n is 3, the other one is 560. 500, 1, 2, 3, 4, 5, 6. Then when n is 4, the other one is 710. So 710, I think 10 is one box. When n is 5, the other one is 910. 910 is one box. When n is 6, the other one is 1110. 6 is 1110. Sorry, it is 1100. So this is going to be exactly this point, 1100. Then I'll draw also the error bars. For the error bars, I'll slightly increase the thickness. You can always pass there the pencil twice so that you make it bold. The first error bar was 20. So 20, those remember each box is 10. So 20 means 2 boxes above and 2 boxes below. So 20 is going to be this one here. The next one was also 20. The third one was 30. So those are 3 above and 3 below. Then the other one is 50. 50, those are 5 above, 5 below. The other one is 80. Those are 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And the last one was 30. Those are 3 above and 3 below. Okay, so of course I'll now draw the lines at once. It's not always good to draw the error bars before drawing the line of best fit because it affects your judgment. So I'll have to rotate this graph. So I will rotate it so that it's on one page. Of course, I know you can't rotate your computer if you're watching on the computer, but you can rotate your phone maybe. So I'm going to try and expand this. because I want a bigger picture. All the points should be on the same, must fit on the same page for me to make a proper judgment. Okay, so let me change the color to, okay, let me use this. Dark blue. So for the line of best fit, I must balance the points. One, two, three, four. Okay, this line can be rotated anti-clockwise. You're trying to ensure that the line cannot be rotated any further. Okay, I think that is a better line which leaves out 1 point. I can even check and see maybe I did put it correctly. When n is 3, the other one was 560. 560. Yeah, that is correct. Okay, then I'll also draw the line of worst fit. So for the worst fit line, I'll use a different color. So I can join the top of the top error bar to the bottom of the bottom error bar. The top of the top error bar, which is here, to the bottom of the bottom error bar, which is here, but make sure that all the other error bars are crossed for the error for this line to be correct. When I do that, almost the third error bar from the bottom is almost not crossed, so I will have to adjust my line so that it crosses into this error bar, which is almost left out, which is the third at the bottom. Or I can also check the one on top, the bottom of the top error bar, and the top of the bottom error bar, and I see that it is also giving almost the same impact. It tends to leave out the third error bar from the bottom, so by all means I will have to adjust and consider bringing that error bar which is kind of getting left out. So I am joining the top of the top error bar so that it goes through this point here, because this is the minimum it should cross through. So it should go through this point here, this one here. Okay, so I join the top of the top error bar and I try to ensure that it goes through this point here, but it crosses all the vertical error bars. That is the line of worst fit. So I'll label, of course I have to rotate this because when I write, people will see this different. Then the next thing I have to also draw the triangle. I'll try to increase this. Let me even change the color. Okay, I have to choose 2 points for which the triangle should pass. You can draw the same triangle for the two lines. For example, I have this point here and this one. Then at the bottom, if it is not easy to find 2 points for the triangle to be the same, you can draw two triangles, or you can draw one triangle and I break it at the bottom. So at the bottom, for the green line, I will take this point here. Then for the blue line, I will take the other point. So at the top, I will draw the same triangle, but I will break it at the bottom. So for green, I'm using this one. And then for the blue, I'm using this one. Okay, so I'm just going to write the read-offs so that finding the gradient is very easy. So for best fit, which is the one in the blue, I have this value, y value there, which is, what is this y value? This is 100, 1000, so it is 1000, 10, 20, 30, 40. So it is 1040 minus the x value corresponding to blue. This value here is 5.1234567. That is 5.7 minus the x value corresponding to blue here is 1.1. Then the y value corresponding to blue is 1, 2, 3, 4, 5, 6, 7. So it is 170. That is for the best fit. Then for the worst fit, the y value y2 is 1, 2, 3, 4, 5, 6, 7. So it is 1070. This is for the worst fit. 1070 minus the x value for the worst fit is the y value for the worst fit is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is 200. So this is 200 divided by the x value is the same here, so 5.7. The first x value for green, the x value is this one, which is 0.1, 0.2, 0.3. That is 1.3. Okay, so I'm just going to write this on paper so that I just transfer them very fast. So we have 10, 40, 170, 5.7, 1.1, 10, 70, 200, and 5.7, 1.3. Okay, so I have to rotate this back so that I write very easily. Okay, so the gradient of best fit is going to be 10, 40 minus 170 divided by 5.7 minus 1.1. Gradient of worst fit was 1070 minus 200 divided by 5.7 minus 1.3. So I'll just press my calculator. I think there was no power of 10, so I don't need to mind about anything. So 1040 minus 170 divided by 5.7 minus 1.1. So this is 189.1. Then the second one is 1070 minus 200 divided by 5.7 minus 1.3. So this is 197.7. Then the uncertainty is going to be 197.7. Let me check it again. 1070 minus 200 divided by 5.7 minus 1.3. It's 197. So 197.7 minus 189.1. So this is 8.6 or approximate, okay, 8.6. So the gradient is going to be 1 9.1 plus or minus 8.6. If you want, you can write plus or minus 9 or plus or minus 10. And this you can write 189. Or I can write 190 plus or minus 10. But this is fine. Okay, so next is the measurement. The student measures the height of the tube. The student's values are 83, 89.2, 83.3, 83.1. Determine the average height. So the average we just add and divide by 1, 2, 3, 4. So it will be 83.5 plus 82.9 plus 83.3 plus 83.1. Divide by 4. So that is 83.2 plus or minus. Let's find the uncertainty. Of course, for repeated measurements, the absolute uncertainty is always half of the range. So this will be a half of the highest. The highest is 83.5 minus the lowest, which is 82.9. So 83.5 minus 82.9 divide by 2. So that is 0.3. Then use your answers to A, C, Roman 3 to determine the value of C, include the unappropriate unit. Of course, we said from A, the gradient was C over 2H, which implies that we are finding C, which implies that C is equal to twice H times the gradient. So this is going to be 2 times 83.2 times the gradient, which is 8, 9. The gradient is 8, so it is 189.1. 189.1. That was the gradient. So this is going to be 2 times 83.2 times 189.1. So this is going to be 31466. Maybe 0.24. They've not asked for the uncertainty here, so I'll just write this. But they said include an appropriate unit. Okay, H is in centimeters. H times the gradient. H is in centimeters. Gradient on the vertical it was hertz. Divide by on the horizontal it was a unit, so it is centimeters hertz. Centimeters hertz, but remember hertz is the same as per second, so it is going to be centimeters per second. It doesn't make sense to say centimeters hertz, but centimeters is per second, so it is going to be centimeters per second. Okay, then determine the percentage uncertainty in C. Okay, so notice that C is equal to H times the gradient. If you're good at finding uncertainties, you'll notice that the percentage in C is going to be the percentage in H plus the percentage in the gradient. So this is going to be the absolute in H over H plus the absolute in the gradient divided by the gradient. Then I will multiply this by 100. So this is going to be, I'll use this space because I want to give another method later on. For H, it was 0.3 over 83, 0.3 over 83.2 plus, for the gradient, I think it was 8.6 divide by 189.1. Then I'll multiply this by 100. 0.3 divided by 83.2 plus 8.6 divided by 189.1. This is 0.1. Then I'll multiply this by 100. So this is giving me approximately 4.9%. So this is 4.9%. That's method 1. Method 2, I've got C. Using the best value, the best gradient. I could also find C using the worst gradient. So C for the best value is 31466. Okay. Then C using the worst values, I'll find this to be 2 times H. My worst fit line was the steepest, so I'll take the steepest value of the highest value of H, which is going to be, I'll say H steepest, H highest, H maximum times gradient of the worst fit. So this will be 2 times H maximum is going to be 83.2 plus 0.3, which is going to be 83.5. That is the highest value of H. Then the gradient of worst fit, I'm using the highest value of H because my gradient is, the worst fit was the steepest line. So I'm using the highest value. So it is 197.7. 197.7. So I'm getting this one here, 2 times 83.5 times 197.7. So this is going to be 33016. So that is for the worst fit. Then it means the absolute in C is going to be the difference. So 33016 minus 31466. So that is 1550. 1550. Then as a percentage, it will be 1550 divided by the best value, which is 31466. Then I multiply this by 100. So I'll say times 100 divided by 31466. So this is giving me 4.9%. So this is going to be method 2. You get C for the best fit. You get C for the worst fit. But look at your worst fit line. My worst fit line was the steepest. So I used the highest value of H. And the highest value of H is adding 83.5 plus 0.3. If I had drawn a less steeper line, then I'll use the lowest value of H, which will be H minimum. So I would subtract 0.3. So I find the absolute by subtracting, then I find the percentage by dividing by the true value times 100. And lastly, the experiment is repeated with a different tube, where n is 2, the frequency is 130 plus or minus 50 hertz. Determine the height h. Remember, taking you back, f was equal to n minus 1 over 4h, I think, then times c. And n is equal to 2, so it means f is equal to 2 times 2, which is going to be 4 minus 1, which is 3, over 4h times c. So we want to find h. So I make h the subject. H is going to be equal to 3c over 4f. Okay. Which is going to be 3c over 4 times f, which is 130. what is my value of C? C is, okay, so this is going to be, H is going to be 3 times 3, 14, 31466. I'll leave out the other part. This part here, it is useless. 31466 divide by 4 times 130. 3 times 31466 divide by 4, 4 times 130. So that is approximately 181.5. 181.5 plus or minus, because they said include the absolute uncertainty in your answer. So for those who are good at calculating absolute uncertainties, for method number 1, the absolute in H would be equal to, I'm using this formula here. 3 and 4 will not affect. So this will be the absolute in C over C plus the absolute in F over F. Then I multiply this by H. So this is going to be absolute in C, which is absolute in C is going to be 4.9. Of course, it will be taking me back, but I can still do that. It will be 4.9 over 100 times the value of C, which value of C is 31466. Okay, then plus the absolute of F is going to be 5 over 130. Then this is still going to be, this is percentage, 4.9%. So this must again be divided by 31466, because 4.9 over 100 times 31466 is just absolute. Then when I divide by 31466, it becomes the fraction. Then again times 31466. Okay, which is the same as just saying 4.9 over 100, because the other one cancels out. This one cancels with that. So I'll say 4.9. Or I would have even used 1550 as the absolute. So 4.9 divided by 100. Then plus 5 divided by 130. Then times 31466. So this is, oh, this is too big. Let me check it again. Percentage uncertainty in C was 4.9%. Okay, the absolute is 4.9 divided by 100 times 31466, which is approximately 151 point that. So 151 point that divided by 31466 plus 5 divided by 130, then times 31466. This is too big. Oh, the other one was in centimeters. Okay, so this is going to be 2752. Remember, this was in centimeters. this was in centimeters, remember? Because this was centimeters per second. So this is centimeters per second. This is per second. This is centimeters per second. So per second has cancelled. So this is in centimeters. So we change this to meters because the question wants the answer is in centimeters. So this is in centimeters. So I have in meters, it is going to be divided this by 100. So this is going to be 27.5 in meters. Then I'll also change this to from centimeters to meters. Okay, I realize there is a mistake here. There's a problem here. First of all, H should be in meters. Here I got it in centimeters, so I have to change this to meters. So this is going to be 1.815 in meters. So this is 1.815 in meters. So when I change here, I first change percentage to absolute. This should be 4.9 over 100. That is fractional. Then times the true value of C divided by the true value of C. So it is this is 31466. So this one automatically cancels out. But here H, I was multiplying the wrong value of H. So this is times 1.815. Okay, let me check this again. So it is going to be 4.9 divided by 100 to change from percentage to fractional. Then plus, answer plus 5 divided by 130. Then I multiply this by 1.815. So this is 0.16. So this will be plus or minus 0.16. Alternatively, I would use percentages, where I would just say, first of all, percentage in H is equal to percentage in C plus percentage in F. Percentage in C is 4.9% plus percentage in C is going to be 5 over 130 times 100. 5 divided by 130 times 100, that is approximately 3.8%. Total percentage is going to be, I said 5 divided by 130 times 100. So total percentage is going to be 3.8 plus 4.9. So that is 8.7%. Then that means the absolute in H is going to be 8.7 divided by 100 times H, which is 1.815. So 8.7 divided by 100 times 1.815, which is approximately 16. So this is approximate, is it 16 or 0.16? Okay, I could use that. Another method to determine the uncertainty in H would be, you would use H, you would use C for the best fit, as we have done in previous part here. And then you use C, of course this is C for the exact value. Here when I'm finding H, this was H for the exact value. So I would find H for the worst value using the worst value of C. Then I subtract the two values to find the absolute in H. In other words, I have H for the best fit, which we have already got. Then I get H for the worst fit. I just replace where there is C, I put C for the worst value. Then I find the absolute uncertainty in H by subtract to find the absolute uncertainty, then you just add it here. So the answer could also be 1.82 plus or minus. I know that this 1.5 was rounded off 3 times 31466 divided by 4 times 130. 3 times 3 1,466 divided by 4 times 130. Okay, so this could also be 1.2 plus or minus 0.16. Okay, I think I've tried my level best. If there is any mistake, you can always write to me. I can try my level best to clarify this. For now, I would like to sign out. Until next time, bye bye.